Good afternoon, everyone. If someone can confirm you can hear me?
Yes, we can.
Yes, thank you, Fatma. Good afternoon. I would like to welcome everyone to our webinar today. It is presented and organized by the EAGE, which is the European Association of Geologists and Engineers, the local chapter in Kuwait. We are honored to have more than 10 organizations present in this webinar. I would like to inform you, though, that this webinar is being recorded and it will be available later on YouTube. I would like to also kindly ask you to hold your questions all the way to the end of the presentation, where the Q&A session will be held. You can either put your questions in the chat box or simply just open your microphone and ask. Now, this webinar today will be about the geomechanics in action, a practical insight into wellbore stability, drilling event analysis, and hydraulic fracturing support. It will be presented by Mr. Viktor Morev, he is a geomechanics specialist that have had extensive hands-on experience in geomechanics. He obtained his master's degree in petroleum engineering from the Heriot-Watt University in the UK, and he has successfully delivered numerous 1D and 3D geomechanical studies across more than 10 countries throughout his career. His expertise includes applying geomechanics to drilling optimization and production enhancement. And luckily, currently, Mr. Viktor is a geomechanics specialist with Kuwait Oil Company, working in the exploration group. Now, after this introduction, I will give the floor to Mr. Viktor Morev to present his presentation.
Thank you very much. Good afternoon, everyone. And thank you to the EAGE Kuwait local chapter to the opportunity to speak today. The title of today's presentation is Geomechanics in Action, and this is exactly how I would like to approach the topic, not only from the theoretical side, but mainly from the practical engineering perspective. We will look at how geomechanics is built, how we calibrate it with actual well data, and ultimately how we use it to support drilling and hydraulic fracturing decisions. So before we go into the workflow, let us first define what we actually mean by geomechanics. So in simple terms, geomechanics is about understanding how rocks respond to stress, pressure, and deformation. When we drill a well, produce or inject hydrocarbons, we disturb the original mechanical equilibrium of the rock. Stresses redistribute, pore pressure change, and the rock responds accordingly. So geomechanics help us to predict that response, whether the rock remains stable, fails, fractures, or compacts after our intervention. As per pictures on the slides, geomechanics today actually supports a wide range of applications across the entire field life cycle, from drilling and wellbore stability to hydraulic fracturing, fault reactivation, and cap rock integrity. And many of the fundamental principles behind these applications were developed decades, even centuries ago. So on the next slide, I would like to take a brief look at how geomechanics has developed over time, and I believe you may recognize some familiar names along the way. So I will keep the history very brief. The main point is simple. Modern geomechanics is built on a few fundamental ideas that we still use today. So the foundations came first. So Coulomb and Moore gave us the basis for the rock failure. Kirsch described the stress redistribute around the borehole, the concept which we are actually using for drilling nowadays. Andersel showed the concept of normal, reverse, and strike-slip faulting. 𝗪𝗪𝗪 and Bayet introduced the effective stress and the pore elasticity. By the way, the concept that are still central to the stress modeling today. Then, roughly from 50s to 70s, we can think of this as a birth of petroleum geomechanics. These foundations and theories started to be applied to hydraulic fracturing, pore pressure, and the reservoir compaction. From the 70s to around 2000, the focus moved towards the well-scale geomechanics, stress orientation from the breakouts, mechanisms of losses, wellbore stability in deviated wells, and sand production. And starting from 2000s, we got better computing and numerical modeling capabilities, and it allowed us to move into 3D domain, coupled and field scale geomechanics, and study compaction at subsidence, study depletion, incorporate seismic, launch unconventional reservoir geomechanics, and even support the CO2 storage studies. So this is pretty much the history of evolution of geomechanics, and today I want to focus more on a well-scale geomechanics and its role for saving tremendous amount of money for petroleum industry. So this slide refers to a survey conducted in 2010s, looking at the major contributors to non-productive time during the well construction globally. Around 65% was linked to drilling equipment, drilling management, or other issues, including weather conditions. Nevertheless, a significant portion of drilling NPT was linked to pore pressure prediction and wellbore stability. For sure, exact numbers will, of course, vary from field to field, and this is a global statistics, but the message is straightforward. Many expensive drilling problems have a geomechanical component. So today, let's focus on this component in more details and learn how we do the geomechanical studies and how proper study is capable significantly reduce the NPT during the drilling operations. So normally we separate geomechanical study into two main parts. So the first part is the mechanical earth model, or MEM. The MEM describes three things: the mechanical properties of the rock, formation pressure, and the in situ stresses. The second part is an engineering analysis performed using this model. So one of the most common example is a wellbore stability analysis, where we use the MEM as a mandatory input in addition to the well geometry and the failure criterion. So this analysis allows us to get safe mud window, provide suggestions for well trajectory optimizations, and casing design. The same MEM also can be an input for other analysis, such as critically stressed fractures, sand production, or perforation stability. So the key point here is that MEM itself is not the final answer. It gives us the foundation for further engineering analysis. And depending on the problem we want to solve, the model can be built in a different scale. So let's have a look at the modeling scaling and modeling sequence. Here at the base of the pyramid, we have the 1D geomechanical model constructed along the individual wells. So this is the step where we establish our fundamental components: mechanical properties, pore pressure, and stresses. So once these properties are understood and calibrated at the well level, they can be propagated into 3D field scale model, incorporating structural components such as fault, fractures, unconformities, and seismic attributes. And when we introduce the time component, for example, reservoir depletion at different type step, we move towards 4D geomechanical modeling. The main point here that 3D and 4D models depends strongly on the quality of underlying 1D models, which is the most difficult part of modeling itself. And for the rest of today's presentation, I will mainly stay at the well scale and will talk through the workflow which we use in 1D modeling step by step. Okay. This slide is essentially the roadmap for the rest of the presentation. We start our workflow with data processing. Then we move into the offset well analysis. So first we understand what actually happened during the drilling. We call it drilling event analysis. Then we build the post-drill MEM with all its components, and we finish with the wellbore stability analysis. So once the offset wells are understood and calibrated, we transfer that knowledge into the plant well analysis, where we can predict stability of the well, evaluate trajectory, and assess risks even before the drilling. So, and now I would like to start the offset well analysis with the most practical question of all. What actually happened during drilling of my offset wells? So we call this process drilling event analysis. And again, this is where we start understanding what actually happened in the offset wells. So first of all, in geomechanics, we focus on identification of losses, gains, cavings, tight hole conditions, and stack pipe. These observations help us to understand the reasons for NPT and help us to calibrate the post-drill geomechanical models. Here on the slide you see the 𝗘𝗃 digital solution, which we call TDR analyzer. Here the events are structured, plotted on the time depth plot, and summarized statistically by formation and by the drilling section. So once we finish the work in DDR analyzer and all the information is structured, the main patterns across the offset wells become much easier to see, the patterns of drilling events. I will give you an example. Here on the slide I have the 7 offset wells and different color codes for the points categorize different drilling events. So in geomechanics we focus on the gas group, which means gain, kick, influx, or any gas spikes, losses, cavings, tight hole conditions, and stack pipe. So the value of looking at the wells together is that if the formation repeatedly generates similar problem in several wells, that immediately attracts our attention. So some repeated patterns. And to make these repeated patterns even more clear, we can switch to the visualization in the table format. So this is exactly the same 7 wells and presented as a table. And this table contains essentially the same information, but by formations. Now we can immediately see where we have some recurring problems. So some intervals are dominated with losses. Others show repeated signs of wellbore instability, like tight spot, cavings, and stack pipe. And in deeper intervals, we may see some pressure-related events such as gas or influx. And the purpose is not to conclude the root cause from this table. The purpose is to identify where we need to focus the deeper technical investigation. So the next step for us is to do this investigation and connect these drilling events to the geomechanical model. Here is the drilling events on the right plot, integrated with formations, lithology, geomechanical model, mud weight, and the casing design. And this is where the drilling event analysis is becoming very useful. Instead of simply saying we had a stack pipe, we can start asking where exactly it happened. What was the mud weight? What was the mud type? What was the safe mud window? And what was my trajectory? So by answering all these questions, we actually kill 2 birds with 1 stone. On the one hand, we deeply investigate the reasons for these incidents. And on the other hand, at the same time, we are improving our offset models to better predict and anticipate similar events in future wells. So now I think we got a solid understanding about value of drilling events. And let's move to the construction of mechanical earth model itself. So the first major component of our mechanical earth model is the rock mechanical properties. The main idea here is that log-derived mechanical properties require calibration, and that calibration comes from the core laboratory testing. So I would like to dedicate a couple of slides to the main laboratory testing techniques, and starting with a very important step, quality control of the test results. So here you see the CT scans of core plugs before the testing. So eventually both plugs will fail during the test, but only one of them will pass our quality control. On the left side, the sample develops a clear shear failure plane. And this is the type of failure we are looking for, and this can be used to support our wellbore stability calculations. On the right side, we see a different non-shear failure mechanism, pore collapse or compaction, and we consider this test as not valid, and we will treat the results differently. So this is one of the examples of the quality check of results of the geomechanical lab studies. And now let's have a look at the main laboratory tests. I would like to start with the simplest and relatively inexpensive test. It's called Brazilian test. Here we estimate the tensile strength of the rock. For geomechanics, tensile strength is particularly useful when we are interested in fracture initiation, breakdown behavior, for example, in hydraulic fracturing applications. For compressing behavior, however, the most familiar test is a UCS test. So the UCS test measures the unconfined compressive strength of the rock. In other words, the peak strength of the rock. In addition, from the stress-strain response, we can derive static Young's modulus or static Poisson ratio. So the limitation is that subsurface rock is normally confined. So the next step is to look at the behavior under confining condition, and we have a specific test for it. It's called triaxial test. It can be single stage or multi-stage. Here on the slide you see the multi-stage triaxial test. So the rock sample is here tested under confined pressures with which actually represents the subsurface conditions more realistically. In a multi-stage approach, the same sample is loaded at different confining levels, and you see them on the top right plot. From this response, we can derive not only strength and elastic properties like from single UCS test, but also we can derive the friction angle and failure envelope. So the next question is how we can use this discrete point data to generate continuous mechanical properties profiles in the well. To manage this problem, we are building correlations between the major mechanical properties, because we want to set the link between the log-derived and core-derived mechanical properties. So using the equations and correlations, we can generate continuous mechanical property profiles. I will give you an example. So here on the plot, you see the input obligatory logs for geomechanics, which are compressional, shear, acoustics, and density log. From these logs, directly, even without core studies, we can get dynamic, elastic properties. But the next stage of getting static elastic properties and strength parameters requires the core laboratory support and study of the core plugs. So the strength parameters which we came up after having equations from the core laboratory studies are unconfined compressive strength, tensile strength, and friction angle. So with the mechanical properties in place, we can move to the next MEM component, which is a pore pressure and in situ stress. This is a huge topic for discussion, and I want to make it short and show only practical examples. And even before showing practical example, I want to clarify some basics about the stress definition itself. So the stress can be described as a direction or as a magnitude. On the left side of the slide, you see the determination of direction of the stress. For this purpose, we can run image log in a vertical well. If we observe the breakouts, this is an indication of the minimum horizontal stress, and if we observe the drilling-induced tensile fracture, this is the azimuth of maximum horizontal stress. For Kuwait, regionally, the maximum horizontal stress direction is 45 degrees northeast, and it's pretty much constant for Cretaceous and Jurassic formations in all country. Another thing which we want to discuss is the magnitude and regime. So we know that there are three principal stresses. So overburden stress, which is simply the integral or summary of the mass of the rock, and two horizontal stresses. Horizontal stresses have two origins. Of course, it's compacting rock under the weight of overburden formations, and tectonic component like mountains nearby your formation. Once we complete the calculation of the principal stresses, we can compare the values of these stresses and understand what regime we are having in situ. So there are three options: normal faulting, reverse faulting, and strike slip faulting as per the Anderson model. And here on the slide you see examples of the normal faulting, reverse faulting, and strike slip. Okay, I think it's clear with the stress terminology. Let's have a look at the example with the actual well. So I want to start from the left side of this plot with the pore pressure profiles. So here is one thing. In Kuwait, we have not significantly big amount of thick shales, which makes traditional method of pore pressure prediction quite limited. So Eaton method of compaction disequilibrium doesn't really supportive in the carbonate formations. So that's why in Kuwait we mostly rely on the direct pressure measurements. And here an example in the well how we put the pressure measurements directly on our pressure profile curve. For sure, we do some 𝗙𝑐, the test which show us the highest mobility, the most reliable ones. And in the intervals where we don't have the direct pressure measurements, we can rely on drilling events and events such as gain or influx. If we're getting gain or influx, that means our mud weight was not able to keep the fluid inside of the formation, and it's also in the indication of the pore pressure which we have in our formation. Another side of the story is stress profile calibrations. So here on the plot, the black line is the vertical stress, green one is the minimum horizontal stress, and the red one is the maximum horizontal stress. So overburden stress we calculate in pretty simple way, and the minimum horizontal stress we can calibrate to the stress tests. For sure, we can use FAT-LOT, but we don't prefer to do it when we have a mini frag test. So during the mini frag test, we are reaching the point of fracture closure pressure, which is a direct measurement of minimum horizontal stress. So at this particular well, we experienced two mini frag tests in upper Mini-Gish and lower Mini-Gish, and use them for the calibration of the stress profile. All right. Okay, so, and this is actually the result, how a final plot for the mechanical Earth model looks like. So it has the input, ready mechanical properties, and pore pressure profiles in as a stress, as a gradient, and as an equivalent mud weight, and identification of the stress regime. Now, at this point, we can use the mechanical Earth model and start answering the engineering questions. For example, under what conditions will the borehole remain stable? To answer this question, we go to the next step in our workflow, which is wellbore stability analysis. The objective of the wellbore stability analysis is to determine under which condition the borehole remains mechanically stable. In other words, what is a safe mud window. Okay, let's consider all components of the safe mud window. This is a theoretical example for us to be on the same page and understand what type of gradients we are getting as a result as a main deliverable of the wellbore stability model. So here on the slide, on the plot, you see the pore pressure gradient. You see the shear failure gradient, or in other words, breakout gradient. We also have the fracture gradient, loss gradient, and the fracture initiation pressure gradient, breakdown gradient. So let's consider case by case what will happen if I drill the well with some particular mud weight. So when my mud weight during the drilling is lower than the pore pressure gradient, I'm getting such events as kick, gain, influx, or in the worst case scenario, blowout. When I decide to increase my mud weight to be higher than the pore pressure gradient, but still lower than the shear failure gradient, I'm getting such events as stuck pipe, borehole collapse, cavings, tight spots, overpulls, and breakouts, which we see on the microimager. Another scenario when I increase the mud weight higher than the fracture gradient, higher than the loss gradient, I start to reactivate existing fractures and may start to get the losses, or if formation is depleted and permeable, I can start getting differential sticking. And the extreme case when my mud weight is so high that it's higher than the fracture initiation pressure gradient, at this point breakdown is happening. It typically results in total loss, fracture propagation. On the microimager, we might see the drilling-induced fractures, and all the situation may end up with loss of well control. So the only area at this plot where we must keep our mud weight is called safe mud window. This area have a lower risk, and no geomechanics driven events are actually expected. So we will try to keep our mud weight within the safe mud window. So this is a concept. Now let's see how it will work in actual well. So here we have the post-drill wellbore stability analysis. For each formation, we estimate the main limits, pore pressure, breakout gradient, loss, and the breakdown gradient. So the ultimate goal is to construct a calibrated geomechanical model that honors all observed instability events and provide a strong match with the caliper measurements and breakout data. So, because the better post-drill model reproduces the actual drilling events, the higher our confidence in its ability to predict and anticipate similar issues in the future wells. So that's why at this moment, when we do the post-drill wellbore stability analysis, we try to tune the model so it's capable to repeat and represent all happened drilling events. At the next slide, I have an example for shear failure calibration. So here we compare the predicted breakouts, which are the red patterns, with the real breakouts from the microimager in different parts of the Rattavi limestone. Here you see a pretty good match, and this is one of the ways for calibration of the geomechanical model and shear failure gradient. So at this point, once we trust the offset well model, we can make the key shift from explaining what happened in the past to predicting what may happen in the next well. So now we move to the planned well analysis, and the objective here to transfer all our experience from offset wells to the planned well. So here on the left side, we have the planned trajectory, and expected formations at this well. On the right side, we see the prognosed geomechanical model and safe mud window along this planned trajectory. For each section, for each drilling section, we calculate the lower and the upper limit for the mud weight, and we call it safe mud window. Here it's worthwhile to mention that mud weight is not only a solution for wellbore stability and solving all the wellbore stability issues. We have another tool, which is a trajectory. So if we understand that the safe mud window is too narrow and risky for drilling some intervals, we check all possible trajectories and in respect to the in situ stresses, because the change of trajectory often significantly increase the safe mud window for some problematic formations. So in case I have very narrow window, I can play with the trajectory and understand what's deviation azimuth would be the most preferable for this formation. In some other cases, we can also do the casing design changes if we understand that the safe mud window is wide enough or too narrow. Here at this example, so we separated the 𝗪𝗁 formation with a separate casing, because safe mud window doesn't allow us to drill together with 𝗔𝗰𝗋𝗃. If we continue to drill 𝗪𝗁 together with 𝗔𝗰𝗋, we will start to get losses and instability issues. So that's why, based on the safe mud window, we separated these sections. All right. And at my last slide today, I want to have a look beyond drilling practices and switch to the hydraulic fracturing support. In hydraulic fracturing support, geomechanics plays two important roles. First of all, we provide all input information for frac simulator for frac job modeling. So there are elastic properties and stress profiles. Secondly, geomechanics supports selection of the frac interval itself and able to eliminate stress barriers and frac propagation and allows to understand what's going to be the frac propagation direction. So this is a scenario where we done the MEM model and suggested the interval for frac job. So as you can see, the upper 𝗔𝗰𝗍 limestone represent a reverse faulting regime and appear to be a stress barrier. So the decision was made to shift the frac interval below in the 𝗔𝗰𝗍 formation, where we have a very nice stress container and strike slip and to normal regime. Once we did the modeling in frac simulator, we saw that the fracture propagation will go down, covering all our target intervals. And this is how geomechanics can actually help for hydraulic fracturing job. And this point brings us back to the main message I would like to leave to you today. So the geomechanics is not a simply set of stress curves or mechanical earth model. The real value comes from connecting different types of information. So we start with what happened while drilling. We integrate logs and laboratory measurements to understand the mechanical properties. So we constrain the pore pressure and in situ stresses with measurements and operational observations. And we calibrate the model against actual borehole behavior. Only after all these steps, we use the model to support engineering decisions, whether it's wellbore stability, well planning, or hydraulic fracturing support. Thank you very much. I also would like to express acknowledgement and thanks to the Ministry of Oil, the State of Kuwait, the management of Kuwait Petroleum Corporation, and the Kuwait Oil Company for granting permission to present selected case studies. Special thanks to the exploration manager 𝗔𝗽𝗽𝗹𝗶𝗃 and GNG Solutions team leader 𝗪𝗂𝗶𝗶𝗵𝗵. Appreciation is also extended to the 𝗘𝗃𝗃 exploration group members for their valuable support and contribution throughout presented case studies. Thank you very much. I'm happy to take your questions, if any.
Thank you, Mr. Morev. Thank you. So if anyone have any questions, please feel free to ask or to put them in the chat box. All right. Any questions?
Thank you, Victor.
Assalamu
Thank you.
alaikum. Thank you so much for the presentation. I wanted to ask if we can get a copy of the presentation.
There are some questions in the chat box. You may please answer.
Do you hear my voice?
Yeah, I think as per EAGE regulations, they will load the presentation as to the YouTube, but for the slides we need to double check. I think it's possible.
Okay, and I have a question, purely geomechanics, about the relation of static Young's modulus and compressional travel time, horizontal maximum and minimum horizontal stress with also compressional travel time, because I found out that they are very sensitive to that travel time. So how would you explain that relationship?
So in geomechanics we have, let me open the slides with course study. So depends which test you are talking about. So for sure we have two types of elastic properties. We have dynamic one and static one, and this is the main issue, and we want to connect them together. So dynamic elastic properties derived from 𝗍𝗶𝗴𝗵𝗹 from the log data, and the static parameters derived from the plots, strain, stress plots. So, and here is an example for when we try to connect Young's model is dynamic and Young's model is static, to connect the log data with the core data.
Hello, gentles.
Yes.
So I have thank you first of all for this fruitful presentation and the slides. What I want to ask about, I have covered almost 3 questions at chat box. The first one is how do you calibrate the maximum horizontal stress, especially that the figure you have showed us showed different stress regime. I have seen one strike slip regime where the 2 horizontal stresses and the overburden gradient is in between, and the one formation showed the reverse regime. So normally, how do you go through validation of the SH maximum magnitude? That was the first question. And the second question is related to the losses related to induced fracture or pre-existing fracture. How are you able to differentiate between them, especially that even the Poisson's ratio as a static values is not reliable, and I do believe most of geomechanics specialists cannot use the static Poisson's ratio as a validation for the actual one to be used for fracture calculations. And finally, I have seen pore pressure values reached to 18 ppg, so you would be Yeah, and it would be good if you just give us more about the major causes about the overpressure resulting in such high pore pressure. Thank you.
All right, thank you very much for the question. I will start with the first one. So for calculation of the horizontal stresses, we are using pore elastic model, and our approach is actually we calibrate the minimum horizontal stress with fracture closure pressure values from the mini-frac, and we keep maximum horizontal stress as is. In Kuwait, we have a pretty high stress regime, so predominantly we have strike slip to reverse at some extreme cases, which I showed you for the hydraulic fracturing support. So we are not using the methodologies like estimation of the breakout widths for calculation of the maximum horizontal stress, because there are anyway all these methods are secondary one, and there is no way to measure directly the maximum horizontal stress. So my answer is pore elastic model, calibration of minimum horizontal stress, and the maximum one we keep as is. Now I would like to refer to your last question, and then we go back to the losses. So you're right. So actually, the high values up to 18 ppg in 𝗪𝗂𝗶𝗵𝗵𝗪 formation. So this is the reality we have to live with. So we have some fields where we had a direct indication, which is gains and kicks with a mud weight of around 18 ppg. So this is actually primary indication for us that we have abnormally high pore pressure. The mechanism for the pore pressure most probably secondary. This topic is still under discussion. So, and yeah, as I mentioned before, predominantly we are having the carbonate rocks and with some minor intervals of 𝗪𝗍𝗪 formations. Going back to the losses question, it's not very clear for me. So we probably don't differentiate the Poisson ratio based on the fractures itself, but can you please clarify the second question regarding the losses?
Yes, please. I'm asking you about the losses rate. Do you have any way to differentiate between the losses related to the pre-existing fracture and the induced fracture one? Just we normally use such type of validation to be used in the design of the hydraulic frac itself. So do you have the luxury to differentiate between the different losses due to many reasons or not?
Yeah. So now it's clear. So we have a pretty wide statistics of image log data in Kuwait, more than 2,000 wells. And we can say that drilling-induced tensile fractures are not common for Kuwait. So that's why it's very rare situation when we reach the breakdown gradient during the drilling and generate the drilling-induced tensile fractures. So all our losses are related to the pre-existing planes of weakness and faults and fractures which originally were there in the well and which we just reactivated during the drilling practices.
Yes, it's a good answer for me, but if it's the real case right now is most of the fractures are already pre-existing, so using the same numbers for the mini frac test will not be easy to be used again in the upcoming wells. So it will not be the same value in the same time. Do you agree with me?
Yes, they affect the fracture closure pressure, but this is the reality which we deal with. Thank you for the good questions.
Thank you for your answer. And one last question, if I have the validity,
Sure.
it looks like that you have the luxury to use very high mud weight exceeding all the shear failure present along the borehole. You have never used mud weight lower than the breakout just to allow some sort of depth of damage just to be able to drill the lower sections, which is carbonates or sandstones, without getting losses, or even trying to not to separate the two holes in one section?
Mm-hmm. Very good question. Let me open the slide with the breakouts. So it is here. So actually having a breakouts during drilling, at least Cretaceous formations, is very common in the drilling practices in Kuwait. So having breakouts and drilling with a mud weight slightly below than shear failure gradient is a normal practice. So the major priority for us keep the mud weight higher than the pore pressure gradient, and in some extreme scenarios, for sure, we recommend to keep it higher than the shear failure gradient.
It's clear. Thank you for your answers.
Yeah, you're welcome.
All right, I have a question. Do we need 3D geomechanics for drilling purposes?
Yeah, very good question. So depends at which stage of development we are currently at the field. So I would highly recommend to do the 3D geomechanics for drilling purposes at the development stage. For example, when we have 20 rigs on the field, it's physically very difficult to support 20 rigs with 1D geomechanical models. And the second reason of having 3D model for drilling objectives is actually when you have very complex reservoir, when you have a lot of fractures and faults which potentially can cause total losses, it's better to have a 3D model to eliminate and anticipate the risk of hitting the fault or system of fractures. In all other cases, I prefer to go with a 1D model.
Yes, understood. Thank you so much. I would like to thank everyone for attending as we come to the conclusion of today's webinar. I would like to thank Mr. Morev for the great presentation. I would like to also encourage everyone to register in our social media accounts and be able to follow our upcoming events. We have certain events that are coming that will be announced soon, inshallah. And again, thank you everyone for attending and have a good day.